All right, good time of day, everyone. Welcome to this new MLIR open meeting. And today we're going to discuss a proposal about sharding framework design for device mesh. And Shengji from ByteDance is going to present this proposal. Shengji?
Yeah, thanks, Maddie. Hi, everyone. This is Chenji Yao from ByteDance AI Compiler team. Today, I will talk about the sharding framework design for device mesh. I know that the current design certainly needs some improvement, but I hope it can serve as a starting point. And once we reach some consensus, we can collaborate to implement the code. Let's get started. First, let's begin with the title. I asked a Google bot and I asked it to extract two keywords from the title. It gave me the sharding and the mesh. So this leads to the pivotal questions. Why is sharding necessary? And why is it designed to operate on mesh clusters? In the context of sharding, I think all of us know that the rising popularity of large language model, which demands intricate data and model parallelism, which is used for the effective distributed training and inference. The request parallelism certainly needs the sharding to assist. And regarding for the mesh cluster, and they actually exist in many real-world scenarios. For example, the TPU pod is a 3D torus cluster. And for several connected NVIDIA DGX bots, they can be considered as 2D mesh clusters. The first axis of the cluster could be the NVLink connecting GPUs within a box. And the second axis could be the infinite band connecting GPUs among the boxes. And we also need to integrating the sharding and the mesh, where we should represent the distributed tensor in mesh. And we also need to represent communications on mesh clusters. Here is today's agenda. First, I will talk about the mesh dialect. It includes the mesh definition and the operations and attributes in it. Then I will talk about the typical workflow in the sharding framework. It's actually a path pipeline. For the definition of mesh in compiler, it is not used to express the connection of devices in physical center. Instead, it actually serves as a tool to express sharding in a simplified yet constrained manner. Let me still use the TPU pod as an example. It is actually a torus, not a mesh cluster. But it is still could be regarded as a mesh cluster in the compiler perspective, because we don't need to actually know the connection in the cluster. And for the reason why the mesh is simplified and constrained, let's take a look at the example. In the left part, it's a 1D tensor with 7 elements, and the tensor is sharded by a 1D mesh cluster with 4 devices. Then there will be only one sharding result, because the sharding in mesh is implicit even. Then let's take a look at the right part. It's still a 1D tensor with 7 elements, but it's sharded by a general cluster with 4 devices. In a general sharding, one device could hold most of the elements in the tensor, and even some devices could hold no elements. So the sharding result is arbitrary. And here I only present one possible result. And the feature of the simplification could help us implement the optimization. And some optimization could even be impossible or almost impossible to be implemented in a general scenario. Then here comes the first operation in mesh dialect. It's the batch cluster op. It is a simple op placed within a module op. And it's, as the name says, it actually represents a cluster, a mesh cluster. It has 2 attributes. The first is rank, and the second is dim sizes. Here in the example, the rank means that the mesh cluster is 2D, or it has 2 axes. The dim sizes mean that the number of devices around axis 0 of the mesh cluster is 4, and the number of devices around axis 1 is 8. So, and we can know that the total device number is 4 multiplied by 8, which is 32. Additionally, the number of devices around some of the axes could be dynamic. Here, for the mesh cluster with 3D, the first axis and the third axis, their device number are dynamic. Here, I let if the dim size is 0 or the dim size is omitted, which is the third axis, then which means that the device number is dynamic. And also, the total device number is also dynamic. And then I defined a new attribute type in the mesh dialect, which is the mesh sharding attribute. It is an attribute type used to convert a standard tensor into a distributed one. Here, I name a ranked tensor type with the encoding of mesh sharding attribute, and I name it a distributed tensor. It has 2 usages. It could be employed in the encoding of a ranked tensor type, and it could also be used in the mesh annotate op, which I will discuss it in the next slide. And this attribute is not designed to be accurate or thorough to describe a distributed tensor, because it's almost impossible to be accurate. For example, if I want to shard the operand of a count, it is possible that the sharded tensor overlapped or non-overlapped. Both of them are valid with the same mesh sharding attribute. And currently, this mesh sharding attribute contains a simple attribute and an array attribute. And the array attribute is actually an array of interarray. let's take a look at the example again. Here, there comes the mesh cluster. It is a mesh cluster of rank 2, and it has 4 devices, which is 0, 0, 0, 1, 1, 0, 1, 1. And we know that the axis 0 is vertical, and axis 1 is horizontal. Then let's take a look at the tensor. It's a 1D tensor with 4 elements. And here, from the mesh sharding attribute, we know that it's sharded in the mesh 0, which defined up here. And here, this arrow attribute means that the tensor is sharded along axis 0 of the mesh cluster. And the axis 1 is missing here. Then we know that this tensor is replicated along axis 1. It might be clear to view it, to visualize it. Here, in the tensor view, we can know that the tensor is sharded into 2 parts, the left one and the right one. And then we know that each element of the tensor belongs to 2 devices. Here, for example, the first element is belongs to 0, 0, and 0, 1. And we know that it's replicate along axis 1. So the second element is here, it means the device ID. So they are different. It's replicate because they share the same element. And we can also view this from device view. Here, you can easily know that the tensor is sharded along x0 because here the index 0 and the index 1 along x0, their elements are different. In the same way, we can know that it's replicate along x1 because here the index 0 and the index 1 of axis 1, their elements are the same. Let's take a more complicated example. Here, the mesh cluster is 3D, and we can find that the simple attribute in the mesh sharding is omitted. Then we will try to use the default mesh defined in the function ops attribute. And then let's take a look at the tensor. It's a 2D tensor. And the array attribute in the mesh sharding is an array with size of 3. It has 3 subarrays. So for the first dimension, it is sharded by the axis 0 of the mesh cluster, then by axis 2. Other matters, which means that it is first sharded by axis 0, and then it is sharded by axis 2. And for the second dimension, it is not sharded because the subarray is empty. And for the last subarray, it means that the tensor is actually a partial sum along axis 1, which means that we need to apply a all-reduced sum on this tensor. Then we will get the whole tensor. Then let's take a look at the second operation, the annotate op. This op offers an alternative way to hold mesh sharding attribute. Because in the first way, the mesh sharding attribute is added in the encoding in the ranked tensor type. but the encoding is optional, and some transforms might not respect it. So it could be discarded during some transforms. Then let's take a look at the usage of the annotate op. Here, its operand and the result are standard tensors. They don't have the mesh encoding. Then let's take a look at the attributes. First, it will hold the mesh sharding attribute. Then, it has an additional required attribute. If the required is true, it means that this annotation is mandated. The compiler should respect the annotation. The compiler shouldn't modify it. If it's false, which means that the annotation is only used as a hint. For example, in auto sharding algorithm, it could be used as a starting search point. For the as a result attribute, I will discuss it in the next slide. Okay, someone's asking questions?
Yeah.
No, we didn't want to interrupt, so please just continue. It's fine.
Okay, okay.
Sure.
Yeah, I think we're debating how some of the stuff is represented, but we should just pull this into a list and probably discuss it once.
Okay, maybe we could discuss it after I finish my introduction.
Yep.
Okay, let's talk about the as a result attribute. We all know that a tensor could be used as a result of an operation, and it also could be used as the operand of other operations. And it is possible that the result and the operands of the same tensor, their shardings are different. And the as a result attribute is used for this scenario. Here in the example, op0's result is used for op1 and op2. And here, I want the result and these two operands, their sharding different. So I have to add annotation for each of them. And here, the annotate op could be used in this way. First, I will annotate the result of op0. It is actually sharded by axis 0 and 1, and its as a result is marked as true. Then I will annotate the operand of op1. Here, it's this annotate. And its as a result will be marked to false. The operand of op2 is the same way, and its as a result is also false. And by the way, here we can know that there will be an implicit altogether between this annotation and this operand annotation, and another altogether around another axis of the mesh between this annotation and this annotation. After the distributed tensor representing, I will talk about the collective communication library operations in mesh. I think the biggest difference between the CCL ops image between other CCL op is that the replica groups are defined by using mesh axis, and the other CCL ops, their replica groups, are usually defined by device IDs. This could ease the comparing of replica groups between CCL ops, which is a common thing in many optimization related to CCL ops. Here, in this example, it's an altogether, and we can see that there is a mesh axis attribute. From this attribute, we can know that the altogether will be applied along mesh axis 1 here, this one. And then we know that the subarray is actually the second subarray. So we know that the mesh the altogether will be applied on tensor. No, it's tensor. It's on tensor dimension 1. And here, the altogether, the operand, and the result of the altogether, their type is distributed tensor. It's actually the standard tensor with the mesh sharding encoding. Here, all use, reduce scatter, and all tool, their usage are similar. Here I just use altogether as an example. And then let's take a look at the collective permute op. Its usage is also simpler compared to other collective or the collective permute op in FAA. In FAA, the collective permute op is defined by a group of source target pairs. The source is device ID, and the target is also a device ID. And here in the collective permute op in mesh, the source target could be defined by using the mesh. Here in this example, the mesh of the operand and the mesh of the result are different. And both of them have 2 devices. So this example means that the part, the source tensor, the part of the source tensor in device 0 of mesh 0 will be sent to device 0 of mesh 1. And the device 1 of mesh 0 will be sent to device 1 of mesh 1. We don't need to specify a lot of device IDs when we define the collective permute op in mesh. And by the way, this scenario could be useful in pipeline parallel. And the collective permute op could have another usage where the mesh of the operand and the mesh of the result could be the same. And I also need to add an additional attribute in this scenario, which is the mesh axis. It implies that the send and receive is applied along this axis of the mesh. Here in the example, it's a tensor with 3 elements. And it's a mesh with 3 devices. So each device has 1 element. And the collective permute means that the elements in depth 0 will be sent to device 1. And device 1 will be sent to device 2, and device 2 will be sent to device 0. this usage could be used for hollow exchange of convolution of sharding. And I will also have a new operation in mesh. It's the local split op. It is used to extract a small tensor locally from a larger one.
Hey, if we can just pause here, Stefan has a question. Might be on your previous slide.
Okay, sure.
Yeah, I have two questions actually. So one is the slide even one further previous. So I was wondering what this mesh.cluster means. So does mesh.cluster define essentially a cluster of machines? So if I have different meshes that have the same configuration, there are still potentially different machines. Is that how I should think about this?
I think they should be defined as different clusters, different machines.
Okay. And then the other question I had for the next slide was, so if you do this permute example, so how do you know what gets sent where? So that wasn't clear for me.
You mean maybe the device 0 could be sent to device 2?
Yes, I mean that could also be a permute you could do.
Yeah, so it's a simplified but restricted way, as I talked above. It is restricted that the device n should be sent to device n plus 1. It's the only way.
Okay.
So it's restricted.
Seems like it will be easy to add an attribute about distance, right? You could support arbitrary. So instead of the device n sends to device n plus 1, it could be device n sends to device n plus x, where x is an attribute.
Oh, makes sense. I can add a new attribute here. It's, for example, it's the stride. Okay, and the stride is the default of the stride is 1. Does that make sense?
Yep. Yeah, I think so. I don't know, Stefan, this is what you had in mind?
Yeah, I just was wondering because the more general way is encoding like communication pairs, right? So I was wondering why you deviated from that encoding. Just because this is simpler, or because this is the only use case you had?
Yeah, because I think we don't need to support the whole scenarios in data parallel or model parallel. They only use part of the communication pattern. So here I simplified it to ease the implementation of the optimization, and some might be even impossible if if I want to support all the communication patterns.
Mm-hmm.
Yeah, I see what you mean, Stefan. We could have arbitrary communication as long as there is like only one entry, right? One send and one receive per device could be encoded as an attribute. That would be also.
But I do get the point that if you limit it this way, you have more structure, and that helps with optimization. So yeah, that makes sense. Thank you.
Oh, because if I specify for example, the source target pair by device IDs, and it is possible that the device IDs are not attributes, they might be values. So it will be quite difficult to compare values in compiler. But in the way of the mesh, I only needed to compare the axis, and the device number along the axis could be dynamic. Also, what's your question, Mandy?
No, you said the device could be a value, but here I thought that we would discuss patterns of permutation over the cluster. And so the only thing we would need was the dimension of the shape of the cluster to describe a pattern of permute.
Yeah, I had also forgotten that they can be dynamic, right? So this could be a dynamic dimension where you don't know the size, and yeah, then this makes even more sense, because then you can't have like a closed form of pairs, because you don't know how many pairs you have, and then having like a structural shift thing. Okay, that's an interesting observation. But if the number of devices is not known, you cannot statically enumerate the communication pattern. So that's that makes sense.
Yeah. So can I proceed?
Yes.
Okay.
Thank you.
Okay. Then let's talk about the local split up. It is quite similar to the extract slice up in tensor dialect. And also it's a simplified way because it is increased, because the split is implicitly even. So I don't need to specify the start index or the length of the slice. Here in the example, this local split out means that, first the source tensor is only a tensor with 2 elements. And the result tensor will only get 1 element from source tensor in each device. Here, the result in device 0 only get the first element from the original tensor. And the result in device 1 only get the second element from the original tensor. And by the way, the operand could also be an already sharded tensor. It don't need to be a whole tensor. It could be sharded. It actually could be sharded or split twice. And there are more operations in mesh dialect. I will only talk about them in brief. Here, first, the mesh IDF op. It is used to get the index of current device along specified mesh axis. And the second, the mesh size op is used to get the device number around the specified mesh axis. And the mesh subcluster op, it is used to extract a subcluster from a given mesh, which might be useful in pipeline parallel. Sometimes we will define a large cluster, and for each stage, you want a part of the largest cluster. Okay, before we jump into the next stage, let's do a bit consolidation. You might be a bit puzzled about the annotation op, the distributed tensor, and the communication op. So what's their relationship? Usually, the annotation op is used alone. Here, I also named the IR with annotate op with the annotation format. And the distributed tensor and the CC ops in mesh are usually together. And this format, I named it with distributed tensor format. And the annotation format could be converted to the distributed tensor format. This step could be called materialization. The materialization, I will discuss it a bit in the next slide. By the way, the communication in the annotation format, they are usually implicit. Here, there's actually an together here between these two annotations, but I don't express it explicitly. And in contrast, the communication in the distributed tensor is explicit. Okay, after I describing the necessary operations and the attributes in mesh dialect, let's go to the typical workflow in the sharding framework. A flowchart might be suitable as an overview of this. First, at the beginning of the flowchart, it's an IR with annotation, with partial annotations. The annotation could come from the mark of the deep learning framework users. It could also come from the auto-sharding algorithm. Then a sharding propagation path will be applied on this IR. Then I will get an IR with fully annotations. The sharding propagation path is usually depends on the get sharding option and the get sharding annotations with two methods from sharding interface. Then a sharding materialization path will come after that. It's used to convert the IR with annotation format to IR with distributed tensor format. Its implementation is mostly based on the materialized method of sharding interface. Then some optimization related to mesh CCL ops could be executed. After that, it's still the distributed tensor format. Then some analysis could be applied. For example, I can know that I can estimate the device memory usage and to see whether it fits the device memory size. And I can also calculate the communication volume. If the analysis doesn't pass, which means that the device memory usage might exceed the size, or the latency doesn't satisfy our needs, then we can go back to modify the annotation format or the distributed tensor format. Then we can go through the pipeline again until the analysis passes. We can run a sharding partition path. It is used to convert the distributed tensor format to an SPMD IR. At this time, the distributed tensor will be converted to standard tensor, and the mesh CCL ops will be converted to those mesh CCL ops specified by device IDs, not like the CCL ops in mesh specified by mesh access. Okay, so we may need to take a look at the sharding interface and some concept before sharding interface. Here, I'd like to introduce the sharding iterator type enum first. It is quite similar to iterator type enum used for tiling interface. Currently, it has three values: parallel, reduction sum, and invalid. Here, invalid means that this dimension cannot be sharded. And I also add the concept of sharding option. It is used as an additional attribute for a payload op. It is also quite similar to the tiling option used for tiling interface. The tiling interface is usually used this way. It specifies the tile size for each loop of the op. And the sharding option, instead, it specifies the mesh axis for each loop sharding. And when combined with the get iterate type and index map, the sharding option can describe the sharding of an op more precisely than mesh sharding attribute. Then let me introduce the shard interface method. The get loop iterate type and the get indexing map are almost the same as those in Tally interface or linear interface. Then the get sharding option, it has default implementation. It is used to get the sharding option of the op from certain annotated operand and results, which might be partial. Then the set sharding annotation, it also has default implementation. It is used to complete the non-annotated operand and results with given sharding option. Both of these two methods are not designed to yield the optimal sharding result. Instead, I want their logic as simple as possible and describable by human language. Then, only in this way, the front-end users could know how will the result IR after sharding propagation be when they marked their partial annotation. The last method of the sharding interface is materialize. As its name may imply, it is used in the materialization part. It also has a default implementation, and it is used to convert the mesh annotated op to distributed tensor, and it will also insert communication op within op if it is needed. Okay, then let's take a look at the sharding propagation path. This path is to complete the sharding annotation for all operations and function arguments. Let's use the example from the paper, Efficiently Scaling Transformer Inference. Here, it is actually a 2D sharding for the MLP part of the transformer block. And let's try to find what will the minimum sharding be if we want the final sharding in this way. And let's proceed from back to front. First, we will find that the output of the graph is sharded, and the result of the second enzyme is sharded too. Meanwhile, these two sharding are different, so we need to add annotation for both of them. Then let's go forward. The operand of the enzyme is BLFYZ. It's correct because the F loop is the reduction loop of the enzyme, and the W out is also right. The F is YZ and the E is X. Oh, by the way, here 0 means X, 1 means Y, and Z means 2. And then let's take a look at the GRU. Here, the output of the GRU is sharding will be BLFXYZ. So the sharding is different from the operand of the enzyme. But here I can ignore this first because it can be optimized in a general path. Let's jump to the first enzyme. Its result, the result sharding is different from the operand of the second enzyme's operand. So we should also add an annotation for the result of the first enzyme. Then it's the operand, it's BLEF, it's correct. And for the WIN, it's EX and FXY, it's correct too. But we find that the activation, the sharding of activation is different from the operand of the first enzyme. So we should add annotation for the activation. Here is the IR after the annotation up inserted. The first annotation is this one, and it actually annotates for the argument. The as result attribute is omitted here, means that the as result is true. So the argument, if we add an argument if we add annotation for an argument, the as result will be true. Because there's no operand for an argument, and the argument is always used as an operand for other operations. Then we will add an annotation for the result of the first enzyme. It's annotated this way. The as result is also true. Then we will add the result for we will add annotation for the result of the second enzyme. It's added this way. The 1, 2 here means that it's a partial sum along axis 1 and 2 or axis Y and Z. Last, we will annotate for the operand of the return up. It's actually the output of the graph. And the annotation could also be added this way. We don't need to use the annotation up. Instead, we could add sharding option in the operation. It's an attribute. Here, we can use the first dot general or first enzyme up as an example. Here, the sharding option just means for loops. How do we shard the for loops of the dot general? Here, the batch size loop is not sharded, and the L loop is not sharded either. Then the F loop is sharded by axis 1 and 2. And the E loop, which is the reduction loop, is sharded by axis 0. And it will result in a partial sum in the result of the dot general.
I have a question a bit about that.
Sure.
Because you made a jump here from specifying the sharding of data until now, as far as I understand, because tensor dimension were mapped to the mesh. And
yeah, the tensor map here, the annotate map to the dimension of the tensor. And here, the sharding option in the operation map to the loops of an operation.
Yeah, that's a bit different, right? So from there, like, it's not clear to me maybe it's an op interface or something, but you cannot really infer anything about the data sharding before after the dot, or no, before there's an annotate, but after the dot.
Oh, this loop. Let me try to understand your question. This loop is actually defined in the sharding interface. Here, front here, it is actually defined in the loop iterator type and get index map here. And here, then we will know that for the dot general, the loop types are parallel, reduction sum, and its indexing maps are as below. I don't know if I answer your question.
Is that enough to infer, like, for example, just with this, we could infer the sharding attribute encoding of the result tensor?
Yeah, for this dot general, it's enough.
Okay. Okay. Thank you. Another question, if you can just go back previous slides, because I just realized something here. Your annotation, the sharding has 4 dimensions. There are 4 groups of array. Oh, no, not this one, the second one, the annotate one here. There are 4 groups, but the tensor has 3 dimensions. Exactly where your pointer is.
It means that the last additional dimension indicates that whether the tensor is a partial sum or not. It might be clear if I go back to the previous slide here. In this example, there are two. The tensor is 2D, and the sharding is 3D. It has 3 subarray, right? And there's an additional subarray here. Here, one means that this tensor is actually a partial sum along axis 1.
And I had missed this. Okay, thank you.
Let's go back to, okay, go back here. Okay, let me proceed. I think I'll finish this slide. And as I mentioned, the 2 format of short annotation or adding short option, both of them can result in the same IR after sharding propagation. And after this pass, all the operands and the results of an operation are annotated. And we can see that there are a lot of annotated ops in this IR. And for the payload ops, for example, the maximum op, it will be added with a sharding option. This might be a bit, this information might be a bit duplicated, but I will show you that they can be useful in different scenarios. But in a bit of slide later, we can take a look at the sharding materialization first. This path is used to convert the annotation format to the distributed tensor format. First, it will erase the annotation op. Then it will convert the information from the annotation op and use it to convert the standard tensor to distributed tensor. And concrete communication will also be inserted, no matter it's between operations or within operation. Here in the example, you'll find that all the tensor become distributed tensor, including the tensor in the arguments of the function. Oh, and here the tensor of the constant means that it has no encoding, but it just means that currently the constant is replicated for all the devices. And the communication will be also inverted between ops or between operand and results if their sharding are different. Here, the altogether is inverted here because the sharding are different. Let's take a look because the altogether is operated on arc0 and then it is used by the first dot general. We can check the annotation format. We will know that, okay, the annotation for arc0 is here, it's fully sharded. And let's check the here. It's actually an annotation for the for the operand of the dot general. It is only sharded by axis 0. So an altogether will be created to fill this gap. Here in the example, there's no communication within an operation, but it could be possible for convolution up where the hollow exchange might be inverted. Then we can apply some optimization related to CCL ops in mesh. For example, all reduce folder paths or all reduce reassociation paths. Here, and in this example, the all reduce decompose path and altogether move down path might be useful. Let's take the old IR first. Here is an all reduce op, and we can decompose it to reduce scatter and altogether. Then the altogether could move down after the maximum op. In this way, the redundant computation of maximum op could be erased. Is there any question? Okay, I will proceed. Then we can
maybe have one question. Do you have many more slides? Because we are over time now, so I wonder if we should,
Oh, sorry, it's almost I don't recognize that. I will be quick. Then
Okay.
I can perform some analysis, including the memory usage. Let's just go to the examples. For example, I can estimate the memory usage directly from the distributed tensor. And I can get the communication volume from the explicitly expressed communication. And I can know that there's no redundant computation because all the axes of the mesh exists in the sharding option. Here is maximum, no reduction computation. But let's see the old IR before the optimization path. We will see that the maximum op only has mesh axis 1 and 2. 0 appears here. We know that it has redundant op around axis 0. And if we pass the analysis, we can perform the partition, which can convert IR to SPMD IR, and it is actually look at the example. we can get the index of current IDX, and then we can calculate what the exact slice is in this device. Then we can use the subslice. And if the physical tensor is already sharded on the device, and we can simplify the IR. For example, here we can directly convert the tensor with 8 elements to tensor with 4 elements, and we can use the subtensor directly. Okay, I've finished my introduction. Sorry, it's already over time.
Yeah, thank you very much. That was very thorough and very, very precise and clear. So a very good presentation. I mean, I don't have anywhere to go, so we can take time for question and people can watch the recording. If we have lots of discussion, we can also schedule a follow-up maybe next week if people want to discuss more. Maybe we can also take it to discourse and first start to see if it's clear enough or if people have questions that warrant a discussion. But let's see if anyone online wants to ask some question right now. Maybe we can discuss something that Stella was just mentioning, right? Whether annotate is more a metadata, which implies to annotate, a result or an operand, or if it's actually more an op, that means like a short distance or now that results in data movement. So would short tensor be a better name for annotate, carrying the intent of what it is? How do you see that?
Sorry, I was just reading the text. Could you repeat your question again? I'm so
Absolutely. Sorry. I was actually trying to carry the question Stella asked on the chat, which is that the annotate operation, the question is like, is it really an annotation in the sense that we add some metadata, or is it more like the intent is more like to actually shard the data, in which case it should be named shard tensor, because it can result in actual data movement?
It is actually more like to add some metadata for the sharding. It's not designed to be precise.
Okay.
Right, but it implies that when in the process of adding the metadata, the transformation that operates on that is expanding it out to include communication and whatnot. It might just be a verbiage thing, but usually when I see something like annotate or a word like that, I'm just like, oh, and an attribute is being added or something, not there's a physical reorganization, or a runtime cost to this. So I was trying to come up with another word.
I think right now it's annotate because it's a metadata that instruct the path that will do the data movement, right?
Right.
That's why it is. But I see your point.
But that answers why previously you would have why it was mentioned there may be redundant ways to add the annotation, to the tensor type or as an annotate op. It's because the annotate op is actually implying a transformation in order to annotate the tensor.
Oh,
Yeah, the reason why there are different representations is that the encoding might be discarded. The other parties might not respect the encoding. So usually you can see that in the first stage of the workflow, it's annotation format. It will not be the encoding or distributed tensor format.
Right, I get that, but when you're actually processing the annotation, what are these are these representations completely swappable? Basically, can I choose to put the sharding annotation on an annotate op, or on the tensor encoding?
Oh, they are not swappable, because I need to combine the annotation and combine it with the materialize method. Because, for example, for the come up, it might I might use hollow exchanger, or it's possible I don't use it. It will be not reflected in the annotation.
Right. So then that means that they're not. It's not just that the encoding isn't transformation safe. It's that this annotate op is doing possibly two things. It's a way to apply the encoding to a tensor type, but it's primarily saying, driving the transformation that's saying, in order to encode this tensor type, you need to materialize this data movement.
Yeah, I think it's a one way,
Right.
not swappable.
Right. So that's why I was just bike shedding the name, is that annotate signals that it's bidirectional, whereas something like shard tensor would indicate that this is a transformation that needs to happen.
Yeah, yeah. So I actually apply transformation or the optimizations on the distributed tensor format, not the annotation format.
Right. Okay, that was that one. There were a couple other notes I took. One on both the discourse thread and some side channels. We think that it would be really nice if, instead of just having one encoding attribute on tensor, we could just ask the tensor type. We could have multiple attributes on the tensor and ask it for the attribute by type or something. So this wouldn't be a change to your specification so much as I think that we should change the built-in tensor type to support multiple attributes and differentiate them by type, so that this can coexist with other things instead of everyone using the encoding attribute.
Oh, sorry, you mean that you would like a new tensor type for the distributed tensor? Not
No. I think in core MLIR, we should probably change, instead of just having the tensor type hard-coded to take an encoding attribute, probably be able to take any number of attributes, and then instead of saying get encoding, say give me attribute of type sharding attribute, or give me attribute of type sparse tensor attribute instead of get encoding. I think we should just fix the tensor type to be able to have arbitrary annotation attributes.
Yeah, because we're already using the encoding attribute for things, and we wouldn't be able to have a tensor that had an encoding specified as well as sharding specified today. And there's many more uses for that kind of additional metadata. So I think this is a really good motivation for finally making it support more than just one attribute, I think.
Yeah, it makes sense. I think we should specify more types of encoding. Actually, we already use the encoding for dynamic shift in our pipeline. The distributed tensor could be another encoding, and maybe their name could be specified.
Technically, there's nothing that prevents the encoding to be a dictionary or an array already today. The problem is the composability of it, right? It's like, what is compatible in terms of, if you make it an array or a dictionary, it's like, how many encoding can you have, and are they compatible with each other?
Yeah, I would probably, if I were spending 30 seconds designing this, which we won't because we'll bike shed it, it's I would just say that differentiate by type, that I can have multiple attributes by type, and I've got an ability to ask for them. But like you mentioned, the composability is the problem. Right now, we've given one attribute that anyone can use, and everyone used it differently. And so we probably need to fix that. We either need to enforce it to be something that composes or not.
Yeah,
I think it'll be hard when plumbing through all the layers to ever have any verification or anything on these. But the alternative today of creating a dictionary and updating all code to support a dictionary, and then people deciding keys and stuff, might be a little bit too far. But I think we definitely, I think what you've demonstrated here with this is a great demonstration of what kind of metadata can live on tensors besides just encoding. But as we see sparsity and quantization and data tiling and a whole bunch of other things using it as well, they're all kind of doing different things, so they don't quite conflict with each other, but they are using that same one attribute. So I think we've got a bunch of different projects that are going on that are doing all of these things, but few things have tried to combine them yet, and I think this will be the thing that makes it hard to actually try combining. I would love to use sparsity and sharding at the same time, and I could not go write code that did that today. That would work.
Or dynamic shape constraints or any other.
Yeah, exactly.
All right, so we're gonna have to work on the encoding.
I mean, we don't have to do it in one step, but I think that this is probably, this pushes us too far when I look at all of the uses of encoding across the ecosystem. This is going to intersect badly, and we probably need to fix that.
All right, any other topic or question from anyone?
There was a question from Chase.
And read it out loud. Unless Chase, you want to unmute yourself and ask. Okay, Chase doesn't have a microphone, so I'm gonna just read it out loud for Chase. When you decompose the dot operation, the example you gave would usually break the dot into parallel dots paired with a single radius. Do you utilize any more advanced parallel gem algorithm like Summa, Cannon's algorithm, or other, scheme?
Oh, in this step, it will not include how the gem is performed. It's just a high-level representation of gem.
Yeah, so I assume that it's in one of the materialization or transformation that any kind of algorithm can be implemented, I suspect, for actually sharding the gem.
Yeah,
Just not showing.
it only represents the gem is sharding in this way, but it doesn't represent the gem algorithm. It should be in the stage after the pipeline of the mesh.
Okay. Well, I see that Boyan has their hand raised.
Oh, yeah.
So go ahead.
Yeah. So I was curious if you can elaborate a bit more on your rationale of choosing to insert this materialization step where you go from the annotation to distributed tensors instead of instead of what is available like in XLA. I know you take inspiration from there, where you directly go from sharding annotations to collective operations in the XLA instruction set. So, could you elaborate a bit more on this?
Yeah, first reason is that the collective communication ops in SLA, their replica groups are specified by device IDs. And here in the CCL ops in mesh, their replica groups are specified by mesh axis. Let me find. So it will be much easier to compare the replica groups between CC ops. this could always usually happen during some optimization related to CCL. And even more when the device number are dynamic, it will almost be impossible to compare device IDs, because when the device number are dynamic, the device IDs are not attribute. They will be values. It will be almost impossible to compare values in compiling time. Do I answer your question, Boy?
Yeah, somewhat. So I had like shared this example of convolution, for example, in the RFC thread. Because intuitively in the first at first I thought, okay, so when you say I annotate the result type of the tensor, right, in the tensor, inside the tensor, like as an attribute to the tensor, this should mean that actually the result of the operation is sharded such and such. But actually, in order for this materialization to make sense, it has to mean that actually this is not the operation exactly like so for example, for convolution, it's not actually a convolution, but it's a collection of convolutions, if you know what I mean, because actually the sharded convolution is the halo exchange plus this collection of convolutions. So it's kind of like I think it conflates the the meaning of the operation is kind of it's not actually the operation, the convolution operation. It's something else, and it wasn't clear to me, at least. It wasn't clear that it should mean something like this, and I was like wondering whether this might create like some problems, but I couldn't find. I couldn't come up with a scenario that actually would be problematic.
Brian, I think you are asking the question that you proposed in the forum, right? So in my understanding, all the sharded op, all the sharding version op is actually a collection of ops on multi-tensor shard. So I think the sharding version of come up is actually the same as other sharding op. So I think all of them are the same, because the distributed tensor actually represents a collection of many tensors on different devices. So I cannot see any difference of come up in your example.
Yeah, but actually, so yeah, and I guess in the end here, where you have the convolution, so the intuitive meaning is that the annotations of the operands, like the sharding annotations of the operands and the result, mean that the result and operands have to be such and such sharded of the operation. But actually, here, like the meaning of the convolution is changed. It's actually not convolution, this operation. What I mean.
Oh, you mean this operation here?
Yes.
I highlight here is not convolution.
Yeah, because actually, right. So the problem is convolution. Distributed convolution is actually halo exchange plus collection of convolutions. So this so this here actually represents not convolution but collection of convolutions that are that are basically sharded. These convolutions like operate across here there is only one axis, mesh axis 0, and it's mapped on one of the image dimensions, if you talk like in the sense of computer vision. So they operate in the so here, like, the halo exchange is already performed, and basically each piece has its border, like the border. Yeah, so if you imagine, right, you have the border in order to perform the convolution, and the other piece also has the border. So basically, it's not convolution. That's what I mean. And here, like this, you have like yeah, basically what the operation means is conflated. At least was for me. And I was wondering, like, whether it might have, like, this can introduce problems. I'm not sure. I couldn't find any, but yeah. So that's what I meant. I don't know if it's clear.
But in my understanding, let's see, use this example. For example, this maximum up, it's also a collection of maximum up, and it actually a collection of maximum up operated on all the devices of the mesh cluster. So I think it's the same as the come up. Could you clarify more?
Well, okay, so yeah, so the maximum operation, so it's kind of element wise, where you don't need to insert other operations. So to decompose it, to operate on a distributed tensor, you don't need to insert the other operations. So I guess it's like more intuitive. Yeah, it's the same. You just shard it element wise. It's done, but the convolution is decomposed into multiple operations. So it's like a problem here. If you have to be like dogmatic, you're gonna say, oh yeah, it's a halo exchange plus bunch of convolution. So almost it seems like you need another operation here to say this is not convolution. This is a bunch of convolutions.
But for the convolution example, I think the additional operations are already inserted here.
Yes.
I don't think it differs too much with the dot general op. Actually, I also need to insert all those for it.
Yeah, it's kind of, you can say it's the same. Yeah.
But here, for this sharding version of dot general, it's still the same as the normal general op, except that the tensor is distributed tensor, which means that it is operated on it is a collection of dot general ops, and it is operated on many devices.
Yeah, but I think the point here is that for any operation that is not purely element-wise, like the maximum, so dot or convolution, it's not you change the definition. Like if you just look without sharding at the definition of a dot or a convolution, it takes the entire tensor and produces the dot, and the result tensor is the actual results. Whereas here, and it's visible on this slide because you have this partial sum shard, right? The 0. It shows that it was only a partial dot that was done, and there is one reduction that needs to be done after to actually complete the dot. And I think the point that was made here was that for convolution, it's the same. Like it's no longer a convolution; it's a partial convolution. Something I'm not sure is like if you can go back to discourse, the other tab, do we see also the partial? In the results, like in the results of the convolution here, the shard, do we have shard on the tensors? On those shard, do they show They don't
So
show that
I've committed
partial-
the Halo exchange before that actually prepares the pieces and insert the borders.
Oh, yeah, in this case, it's before that it happens. It's not after. So
Yeah.
for the dodge,
because it's quite a lot than I want.
it's visible in the type, I would say, for the dot, and here it's not.
Well, it's visible in the so the input. Well, actually, I made a mistake here. It's it shouldn't be 640 the dimension size, but it should actually include like the borders of the two pieces. I wanted to actually fix it, but it was like, I don't know, maybe after some time has passed, you cannot edit comments. Yeah, so it's I mean, so basically the way I understand it, if you have, for example, like the sharding attribute of the operation, if it's present, it actually changes the operation. It's not the same operation anymore. It's I don't know. So I don't know, like if it's going to be always the same thing, but basically it says apply this operation on each of the shards, something like this.
Yeah, in this other thing, that's right. Because we need to combine the hollow exchange and the sharded version of the convolution, and also we might also need to maybe an altogether after that, after the convolution. Then all of these ops, they together, they will work as the original convolution on the whole tensor, right? The short version of convolution is not enough. It doesn't reflect the overall logic of the original convolution. Is this what you mean?
Yeah, but so there is like I think we have missing terminology, because you have the sharded version of convolution, and like intuitively I would say, well, you mean convolution that is sharded, but this is not sharded convolution. Like it's something else.
Yeah.
Because the sharded convolution is actually the decomposition of all of them. So it's just like we need like proper wording for us to distinguish between the two.
Yeah, that's a good point, because original convolution is defined on the standard tensor. Now you want to extend it to the distributed tensor. So we need to give it a clear definition, right?
Yeah.
Okay, I will add it. I
have also one other, like more of because I think, at least for me, I would contribute to this effort, and like would like to organize like where the source code is gonna be, like for the PR to work to be upstream. Right now, you have a PR in your byte.ir repository, and so we can collaborate basically to work on a single feature branch and stuff like this. Yeah.
Yeah, thanks for your interest, boy. I think we can contact with each other by Discord, which is more real time afterwards, and we can talk about more.
Okay.
All right. Well, I propose that we may leave it there for today. We are like already half an hour over.
Yeah.
Can we take 30 more seconds and say what the next steps are here? Because I think that there's a lot of energy going in this. I'd like to know kind of what are the next steps to deciding how to upstream, how to whether to upstream, all that stuff. Do we need another?
So do you have a proposal? I mean, I forgot, Chengji. How do you want to proceed here? Do you see steps in which you want to contribute this? What are the design points we need to solve before you can start this? I mean, the easier thing is like first one PR that had a dialect, a new dialect, which is mesh, and that does nothing, right? Or that just has one attribute. But but then there are a few things to discuss about some of those specific attributes maybe, and the interface. So how do we structure that?
And currently, I actually have implemented some prototyping code for this. And I put all the attributes, and of course this up on the mesh dialect. And I also put the interface here, the short interface,
Yep.
also on the mesh dialect. And actually, I also add a distribute tensor interface, which I didn't mention here in the slides. I also put it on the mesh dialect. Actually, all of them currently are on the mesh dialect. And I also, for the implementation, for the short interface implementation, I currently use MHO, and I put it on the folder of MHO in our own repo. But it could change. For example, if I want to contribute to upstream, I could put it on the TOSA folder.
Yeah, I think it would be good to do three things. One, and we may, because we're over time, we may need another discussion on, are we ready to start development on this upstream? But assuming the answer to that is yes, then getting the dialect defined, and getting some initial things in there that let us use upstream pieces like TOSA would be really, really useful. And be good to do that before we get way more code written on a branch that then is going to need to be decomposed and landed incrementally.
Yeah, so Chengji, what I meant is we probably don't want to take large patches together. I think your end state is probably not far from where we want to be. And so when you have bullet points, you can almost imagine that each of those bullet points is a different PR. And I haven't looked in detail, but that's the first thing is probably the mesh dialect with the cluster up on the sharding attribute. Or maybe the annotate up, maybe the first 4 bullets is the first good contribution on the slide, the slide here. I don't know if it's a valid way of decomposing things, but that might be something we can review and chew in one bite. I don't know, Stella, if this is the kind of thing you had in mind right now.
I'm just trying to figure out how we give guidance to get something going here. That it makes sense to me.
Okay.
I can understand. I think for the steps, first I can add these 3.
Yep.
The 2 operation and the 1 attribute first. Then I can follow the workflow of the sharding framework. First, I can add a propagation path, and which needs the sharding interface. So I will add the sharding interface first, and then the sharding propagation path.
Looks good.
I will add materialization path and some optimization. Then I will add sharding partition path. I think all the paths could be added one by one, and the necessary part could be added along with the paths. Does that make sense?
That makes sense to me. That seems like pieces that are small enough each that we can review them and integrate them and iterate on all of that. And I suspect most of the discussion should happen probably on those individual pieces in isolation anywhere. I remember we had question while you were presenting at the beginning. Now maybe if we can take a bit more time on that. The mesh cluster of, you're using a symbol, and I was wondering, why is the mesh cluster not an attribute itself?
Oh, because I'm just worried that it will be too long for the tensor type. If it's attribute, I need to place the rank of the cluster and the device number of the cluster everywhere. It will be too long.
Yeah, I like the symbol approach, because what we found trying to lower HLO, which did have it on every single op, is we ended up needing a pass that basically walked the entire program and tried to find all of the ones that were, because at the end of the day, the cluster is representing some resource, some collective communication channel that you have to open, you know, a whole bunch of stuff. And so at some point you have to go find all of those that you need and then build the set you need and then initialize those resources and manage them and do all that stuff. And we just found at some point we always ended up going to the form where they were symbolic like this. So I think it's convenient if at this level of transformation it's useful for you. I strongly agree that it's a great thing. I would love to delete that pass from the HLO side.
So
it's a different motivation than what you were saying though, right? I think I heard originally a motivation about like the IR readability more than a practical thing, for which there are attribute aliases, so which I was about to object. But Ben makes a more practical actual point on that.
Yeah, what I was trying to figure out was if there is actually a you know, if it's just representation, how the IR is spelled, that's one thing. But is there a reason to indirect here? And if there's a reason to indirect, then we should allow that. I'm not sure that symbol ref adder is the right thing to do there. It might even just be a string adder. Symbol ref adder usually implies a scope that it exists in, and attributes don't live in a scope. So it was just a nitpicky thing of I don't know what that means.
Yeah, that's a good point, because if you're in an isolated from above scope deep down below, then you wouldn't be able to reference the cluster at the top level with a symbol ref adder. I don't think
flat symbol ref adder. I think this needs like a few minutes more.
Yeah.
Spelling of it, and we could even do it post landing like it is, because there's not going to be a lot of code on this. We can look at it and poke at it.
Yeah, I think the thing, you know, that there's the from the front ends all the way to where you need the actual things. There's definitely room for multiple different things there. Having a symbol in the IR that we can run symbol DCE on and things like that is super useful, but that doesn't mean it's useful all the way through the pipeline.
Well, and it doesn't necessarily mean that you can legally use that as an attribute on a type, which is what we'd be doing here. Like that doesn't have meaning. The resolution of a symbol ref is when it's anchored on an operation.
We use symbol refs in adders and stuff. Like
we skate on that a little bit, but anyway.
Types only matters when they are attached to an SSA value. So you always have a scope with a type, because you never manipulate types in the abstract world.
True, but
yeah.
then now I've suddenly got, like, if I'm using the same type across two functions and they're in different scopes, then I have to change I have to have a physically separate type if the symbol namespace doesn't match up. Anyway, this is weeds, but
yep,
that's good points.
Is it possible that I put all the symbol in the outermost module op, then all the operations could fetch the symbols? Isn't that impossible?
No, it works.
Yeah, that's fine.
Okay.
Sorry for the nitpicky how IR is spelled stuff. This is like the least important parts of the design, but tends to be infectious.
Something I was wondering about the symbolic things, and that doesn't seem to be the motivation, but I was asking in the chat was, is it possible to describe the IR and then change the mesh? Like how much coupling there is right now between the actual, not the rank of the mesh, but the actual size of the mesh and the IR?
I have yes, there's an op that can get the size of the mesh. Actually, the device number along the specified mesh axis.
But that's an op, so it's dynamic, so it's fine, right? Meaning, could we have a mesh that is incomplete? Can I define a mesh where I just say this is a mesh of rank 3, but I don't give you the dimension right now, and I can still express the entire IR, and then later?
Of course, you can just here.
Yeah.
Omit inside it.
Because that's a very good reason to have this indirection. it means that we can have a piece of IR, and then I can instantiate a machine with 8 GPU or a machine with 16 GPU and just change my mesh, right?
Yeah. In this way, we can analyze, for example, the communication volume symbolically by the number of devices, and maybe we can get a formula of communication volume, and maybe we can figure out what is the best device number to get the best throughput or latency.
Makes sense. Okay, no, that's very good, very interesting. All right, anyone else want to chime in still, or can we actually close this for today?
Maddie, do you think that this is formed enough that we can just post a summary on Discourse and say we'd like to get moving on this, or what do you think?
I'm in favor of this personally, but
yeah, I mean, obviously anyone can chime in and say they're not, but
yeah, I think overall I haven't heard any strong concern today. There is Boyan who may have more comments, but I suspect this can be discussed during the code review. I think the overall design seems to be satisfactory for everyone. And there's no surprise. I think it's also very much grounded in the experience from XLA and other previous work. So for me, it's like we're good to go. But I could also be missing something. So if someone wants to, do you want to post a summary, Stella, or I can do it also if you want?
One of us, either the author or you or me. I'm just interested in getting a path that we
Maybe you can ask Chengji, do you have a timeline on which you think like, I don't know how busy you are with other things. Like if we say like, okay, we're interested by your contribution, how do you see that? How long before you get the first 3 bullets you showed us before?
You mean the
dialect, the sharding attributes, and the cluster of?
It could be finished in a very short time because they are almost finished in the prototyping code.
So we're talking about a matter of a few weeks, right?
Yeah.
Okay. Yeah.
Let's do it.
All right. Let's follow up on this course. If needed, we have slots next week. Also, we can also meet again just to discuss details if there's any hiccup or anything more to discuss. But let's see how it goes.
Thank you.
Okay. Thank you.
All right, take care.